So here's a really important property of bases. You could call this an equivalent definition, I suppose. But this is a characterization of bases that we will make great use of. Here it is. A collection of vectors in V is a basis for that vector space, if and only if every vector in the vector space is uniquely expressible as a linear combination of those vectors. So unique expressibility is the big idea here. Bases have this property that every vector is uniquely expressible as a linear combination of those basis vectors. Okay, so let's see why this is true. Again, you'll notice this is an if and only if, so we have to prove two different things. We'll start off by proving this. So in other words, we are assuming now that our collection of vectors is a basis. And I need to show that every vector is uniquely expressible as a linear combination of those vectors. So, right, well, the span requirement gives me half of that. I know that every vector in the vector space can be written as a linear combination of those vectors because that's what it means for a collection of vectors to span. So the uniquely expressible is what we want to worry about now. So how do I know, given a vector V, and it can be written as, let's say, this linear combination of our basis vectors, maybe I can write that same vector as a different linear combination of the exact same vectors. So you'll notice what we have here. These are the same vectors, V1 through Vn. Maybe, possibly, instead of using those coefficients, I could use those coefficients and get the exact same vector. Okay, so how do we know that this isn't possible? And this is what we want to eliminate because we want to be able to conclude uniquely expressible. Okay. Well, here's the thing. If this were true and simultaneously that were true, then I could subtract those two equations from each other, and that gives me this. And, of course, V minus V is the zero vector. And what that means is then that we have a linear combination of these basis vectors. These are known to be a basis. And this is a linear combination that adds up to 0. And these being a basis, this list of vectors is independent, and that means that these coefficients must be 0. As an independent list of vectors, independent means the only relation is the trivial relation. So those coefficients are all 0, and that means that those numbers are all equal to those numbers, and therefore these are not actually different linear combinations of the basis giving me V. These are exactly the same. Exactly the same linear combinations giving me the same vector. So that shows this uniqueness of this expression. The only way to write V as a linear combination of the basis vectors is exactly that same way. Okay. All right. So now keep in mind that was half of the proof. We've proved this half. And now let's go the other way. Now we're going to assume unique expressibility, and we need to show that this list of vectors is a basis. Okay. So we get to assume that every vector is uniquely expressible as a linear combination of our list of vectors. All right. Okay, so how do I know that this list of vectors spans V? Well, every vector is expressible as a linear combination of these vectors. That's exactly what it means for that list of vectors to span V. Okay, so we're halfway there. Now, how do I know that this list of vectors is necessarily independent? Well, this comes from the uniquely part of the unique expressibility. In particular, if every vector is uniquely expressible, so is the 0 vector. On that list of vectors that are uniquely expressible, the 0 vector is included as uniquely expressible. So there's only one way. There's only one list of coefficients that could possibly make this equation work. certainly the trivial coefficients will work. That then is the only way to do it. That means the list of vectors is independent. So we've shown that this list of vectors spans and it's independent, therefore it's a basis. Okay, so we've proved this theorem now both directions, and we have now a new sort of characterization of what it means to have a basis. A basis is a list of vectors that gives you unique expressibility. Everything can be listed, can be written as a linear combination of those vectors in exactly one way. Okay. All right. So this motivates a definition. This is a definition and notation. We're going to define what are called the coordinates of a vector relative to a basis. And it's exactly the numbers that we just showed exist and are unique. Given a basis, given some vector, there is exactly one list of coefficients to write that vector as a linear combination of those basis vectors. And those numbers we define to be the coordinates. So here we go. If you have a vector V in a vector space, and if you have a basis alpha, then what we call the coordinates of that vector with respect to that basis are whatever these coefficients are. Whatever the coefficients are that you have to take of those basis vectors to get the vector in question. Okay, and by the theorem on the previous page, there is exactly one way to do this. There's exactly only one way to write V as a linear combination of the basis vectors, and those are the coordinates. Coordinates of the vector. All right, so another way to say this is we have this notation. This notation, the square brackets say coordinates, the subscript says with respect to which basis, and this is just another way of saying that. Okay. All right. So we can see now the other half of the reason why we call the standard basis vectors the standard basis vectors. Because look at this equation. Now this is old news. We know that we've made the observation before that curiously the vector AB, when you write it as a linear combination of 1, 0, and 0, 1, those coefficients are AB. How about that? Well, interpreted then as linear combinations of these standard basis vectors, what we see are that we see that the numbers that we've always called the coordinates of the vector, namely just the numbers in that list, those are the coordinates in this sense Those are the coordinates in this sense here of the vector with respect to that basis. So this basis is the unique basis that has this property that the coordinates with respect to that basis are the classical coordinates of the vector. So thus making it a great choice for a basis, and that's why we call this the standard basis. It's a basis because of satisfying the requirements for being a basis. It's the standard basis because of this wonderful convenience. Okay. All right, so that's a digression. Let's go back to coordinates. Here we have a basis for the vector space of polynomials of degree at most 2. Now, there's some details to be checked there. One must check that this trio of polynomials has the required features. Got to check that this spans the vector space of polynomials of degree no more than 2. and one must check that this is an independent list of polynomials. So there's two significant things there that need to be checked, and those would be good exercises for students. So make sure to do that, thus confirming that this is indeed a basis. Okay, so that having been confirmed, here's a vector in that vector space, and let's ask what are its coordinates relative to that basis. And reminder, now this is a vector in the vector space. This is a basis. All right, so going back to our definition, we have a definition of what these numbers are. The coordinates of a vector with respect to a basis. Coordinates are the coefficients. They're the coefficients in the linear I did the wrong color there. The coefficients in the linear combination of the basis vectors that gives you the vector in question. So this is a linear combination of these in what way? So what are these coefficients that make that a linear combination? Those coefficients are called the coordinates. Okay, so said differently, now we just need to solve this equation here for C1, C2, and C3. Do keep in mind that this has to be true for all values of x, so we're not solving for an x here. We're not looking for an x that makes this equation true. I need this to be true for all values of x. And the only way to make this true for all values of x is if the like coefficients are equal to each other. So let's think about like coefficients. Where are the x squared terms? Well, on the right, there are 3x squared. That means that on the left, it better be 3x squareds. So this equation here comes from equating coefficients of the x terms. Okay. Similarly, let's count x terms. There are 2 x's on the right, and there are, well, now let's be careful here, there's minus C1 and C2. Those are the x terms that are on the left. So again, if these are going to equal to all values of x, equal for all values of x, we need these x coefficients to equal, and so we need for that to equal to that. Likewise, for the constant terms, we have C1 minus C2 plus C3 on the left. That had better equal to the 5 that's on the right, and thus we get this equation. So altogether we have 3 equations and 3 unknowns, and you solve for C's. And they turn out to be this. Exercise for the listener. And so keep in mind what those numbers were. These numbers that we just solved for, those are the coefficients, and thus the coordinates. So that's what that is.